Okay, so hi, welcome back. We are again going through this paper here. That's the archive number 1904065056. Yeah, so it's the Quantum Engineer's Guide. And what did we do last week? We discussed more or less what it would take to read the whole paper. So those scribbles here were kind of my estimates for how long it would take. So 10 hours maybe for one section and 11 hours for another. I think we arrived at something like maybe almost 20 hours or something. So what we covered last week was jumping through this, and I was just maybe trying to give a little bit of complementary information on the detailed reading. Yeah, so the idea is that the paper is just meant for people to be reading through, but because it takes maybe up to 30 hours of fresh reading, then that's why the complementary tutorials that we are discussing. So what did we do last week? We skipped for most of the introduction. One important thing to know is the flux variable, which then later will be quantized, and it's defined here in equation 4. And basically, you can think of having some circuit, maybe like this, and then here there will be some grounding, and here I could add some time-dependent voltage. So at this node, I would maybe ask about this integration in the circuitry. Yeah, we are not discussing too much about what this thing does or how it arises and so on. Trying to erase this. But basically, you should have the physical understanding that if there will be some quantum current circulating in the circuit, then the current has a dual description that there's a magnetic field threading through the loop, and that gives you the flux. Okay, so that's why in superconducting qubits, if we have connected circuits, there will be some superconducting currents running through, and there will be this kind of magnetic field involved. And because it's quantum, then there will be some quantization condition on all those fluxes as well. Yeah. So basically, we were looking through different examples of what would be happening if we consider harmonic oscillators of this flux, magnetic flux variable, and so on. Trying to now zoom out. So we were skipping ahead a little bit, but basically, it's not so important. It's not so important to really have a detailed understanding of why this and not something else. If you want to know why this and not something else, Gerwin, under this name, has very good notes. Okay, so that's more like the physics lecture notes for how this kind of stuff arises. And in the meantime, there are nice papers on quantization of all those superconducting circuits. So for example, there's a package that we will be discussing, SQ circuit. It has an accompanying paper. And basically, if you want to know more besides just reading through this kind of discussion of Poisson brackets and the descriptions of the system, then those kind of papers are helpful. Okay. But it's not essential to do all this stuff. So in the end, what happens is that there will be this quantization condition, and this phi variable will become a bosonic variable, And if we will consider linear elements of the circuit, then we will have a harmonic oscillator model, finito. Yeah. So depending on what kind of physicist you are, like at which stage you are working, you maybe decide to look more into this. But for example, for some quantum technologies and for some control and so on, you don't need to know all the details of this quantization. Yeah, you just need to understand where it's coming from, where this phi is coming from, that it has those bosonic conditions, that this is the physical model. So for example, here, let me zoom in. It's not so important to know all the details of this, but for example, here we need to be able to read off that if I would quantize this, then this would be my a b squared plus b x squared harmonic oscillator. So this will be kind of canonically conjugate, right? And then this is important because square root ab is our frequency. So I directly get that square root ec and el, which are some hardware parameters that will give me the frequency of the qubit. Okay, so those kind of things are important at all stages, I guess, but not very essential to know everything depending on your applications. Okay, so for example, here you see what I just wrote. Okay, so those kind of things are important, and in previous sessions we went more or less paragraph by paragraph, and I was giving some comments. Here in those scribbles, I was, for example, explaining the chain of the development. So starting from hardware, this quantization stuff, then effective model, putting some nonlinearity. Then this is important that the transmon qubit has an energy spectrum which is anharmonic. This anharmonicity is super important for coherence properties of the qubit and so on. So this kind of picture pops up a lot. So this section is, I think, essential for reading through line by line to know all the nomenclature. I had in the meantime one question, which was a very good question. For example, do we need this Duffing Hamiltonian and so on, which is kind of taking a fourth order approximation, and I answered, like, we will not use it, but some people use it for research. For example, if you want to derive those unharmonicities, then you study that model. Yeah, there's always time to refine the reading. That's why we are going so broadly. Okay, one thing that is essential is that in the circuitry, it depends how many Josephson junctions you put. The Josephson junction acts as a nonlinear inductor. That's important. So basically, despite having this quantization going on, superconducting qubits you can model as LC circuits, and a Josephson junction is like a nonlinear inductor, and it will have two parameters, which will be its sort of charging capacitance and inductance. Okay. And it really depends how many Josephson junctions you put, and that gives you the notion of a split transmon, which is a wonderful development, and so on. You can try to read this section from the perspective of me telling you that it's a wonderful development. You won't find those adjectives here, right? But you will see the equations that make it really very appealing and very helpful to split the transmon. When you split the transmon, meaning you have two parallel Josephson junctions, you will have two flux variables, but there will be the loop, which gives you the flux quantization. And we are quantizing towards an integer value, but there will be also the flux bias. The flux bias is important because we can steer certain properties of the qubit. So I was saying that this is becoming important for controlling the qubit. Yeah, so those kind of equations are relevant. When you read through, for example, I see this equation here, we didn't cover it in detail, but you can try to understand how this model becomes this model, what needs to happen for that. Those kind of questions you can ask yourself when you're reading. Okay, so this is a picture of both for you to think. If you were in the last session, this is fluxonium. because if I will split it like this, then I have one Josephson junction here and a lot of inline on the other side. So this is this C-shunted fluxonium here. There are four different qubit designs that you see in the picture. A symmetric transmon is basically a transmon which normally would have, the most basic transmon would have a capacitor and a Josephson junction, but because every Josephson junction has also some charging capacitance on this, so CJ, then instead of taking this, you can do this, and that will be a symmetric transmon if the Josephson junctions are the same. In hardware, anyway, they are not the same, and it can be a good thing because that's the asymmetric transmon. So it's not really a zoo of things, it's actually logically connected. When you will be reading the paper, probably you will get lost, but try to understand like what changes what and what do you get from it. And for example, the captions are very well written and they will explain to you what are the features. Okay, then it turns out that those energies, so for a transmon, the unharmonicity is problematic. So you start making it asymmetric, splitting and making fluxoniums, and suddenly you have qubits which are less susceptible to noise. Okay, so basically on this axis is more or less complexification of the designs, and that was kind of needed to try to design better and better qubits. I think the status now is that the fluxoniums are not really yet, you know, the qubits that are being regularly used, but I believe, for example, IQM is splitting transmons, for example, yeah, because then you can have tunable qubits. Okay, those kind of things are important. Then you start seeing, okay, even if I split a transmon, I will have a Hamiltonian that is mimicking a regular transmon. If I have an asymmetric transmon, then I have equation 22. All those are complications, but you can just continue reading and things will be fine. Yeah? Okay, I wasn't checking the chat. There is something in the chat. What causes the quantization in the circuit? So everything is quantum all the time. That's basically a philosophical statement about nature. But it's a much simpler statement when you cool down. So basically you take those kind of circuits for whatever, there's some Josephson junction and there will be something that acts like a capacitor. So let's say that in hardware, this picture is not exactly how it's implemented in hardware, but let's say you have this in hardware and then you put it in a fridge where you have maybe liquid helium. So you cool down to millikelvin. What's going on is that there is a fluid of charges, yeah, because it's a superconductor at those temperatures. The charge carriers are Cooper pairs, but Cooper pairs are made of electrons, so you can still say there's electrons there inside. And those electrons are very repulsive. So it's a little bit like having a rigid crystal because it's 1D wires more or less, and those electrons are charges. So unless there's a lot of screening, they have fairly long range interactions. And now you're cooling down. And basically there's something called the BCS gap. So for this, again, I would maybe refer to Gerwin. So it's called lecture notes on quantum cavity, quantum electrodynamics. I think it's called something like this. So it's lecture notes from Gerwin. I will link it this time in the video as well. And basically, he has a very nice paragraph really explaining it physically. I don't know if I can reproduce it now, but basically the statement is because the BCS gap is, let's say, I don't know, less than 1 Kelvin or more than 1 Kelvin. I don't remember the number. If this is millikelvin and if this would be a Kelvin, then basically at those temperatures, you're more or less around the ground state. And the ground state is not the ground state because you can have different phase quanta, flux quanta trapped here in the loop. Okay, so basically what it means is that this superfluid in the superconductor is kind of looping around the loop. It's kind of circling around, sloshing around in different ways. So the different flux quantum states might be actually currents moving like this, but it can be also oscillators going back and forth. So it can be actually some mode like this. It doesn't have to be a rotating mode. Could be also some sort of sloshing mode like this. And how physically those modes look like, I cannot tell you more even. And I don't know if you need to know more sometimes, okay? But basically, you put it in liquid helium, it becomes very cold. It becomes so cold that there becomes, you get basically the superconducting gap. So the thermal state becomes more or less a ground state. And there's a few of those ground states, and those ground states are more or less numbered by those flux quanta. And that gives you those discrete levels, yeah? So basically this occupation number of the qubit in the harmonic oscillator. If we look at the model that we have somewhere here, okay. So this occupation number n here has an actual meaning in terms of the physics of the system, okay? And it will be related to this quantization. So that's more or less causing it to be quantized. It's basically if you cool it down sufficiently well, which you can do fairly nicely now with dilution refrigerators, then automatically only very few quantum states show up. And to account for those few states that show up, you do quantum modeling of the whole circuitry. Okay, so those quantum effects are always there, but they behave semi-classically at higher temperatures. That would be maybe one statement. So the quantization, you could say, is always there, but it's relevant when you cool down. And that's why we quantize in this case and not for like circuitry in your smartphone. There it's semi-classical physics. Good. That was a good question. You can check, for example, whether that fits with what I'm saying here, whether it fits with the lecture notes and whether it fits with the review. A review will not be explaining things unless it's very, very relevant. So that's why it's sometimes hard to read a review. That's okay. You just read through. And if it's very essential, you go back or you just read somewhere else. Yeah. So I'm reviewing the review, right? So I'm also not giving you the details. And yeah, so basically a review is kind of accounting for all the things that exist in our knowledge. And so it might not be very pedagogical, but this one is actually effectively doing it as well because it's fairly complete. Okay. So anytime something like this happens, that the review here, this guide doesn't explain to you why this quantization occurs, the first thing to say is like, I trust them that it's and then continue reading, because checking everything can come later. That's my recommendation. Trust what well-written papers say, and then see whether the implications are good, and here they are good. And then you can deepen the knowledge. So don't let it distract you. If it suddenly shocks you that there's some quantization, just say like, okay, there is this quantization. Okay, so let's get going. Sorry, I'm scribbling all over the place. Okay, so towards larger anharmonicity, we kind of talked about that for fluxonium. And we don't have many scribbles here, which is good. And we will be talking about subsection C, interaction Hamiltonian engineering. Okay, very nice.